Hello everybody, my name is Rob Brown. I'm the engineering trainer here at Allied, and we're here today at HARTWIG down in Houston, Texas, running on an Okuma MU-6300V to show you a variety of different Allied tools in a material that can sometimes be a little bit of fun. So to give you a little bit of background, the machine, as I said, is an MU-6300V machine. It's a 30 horsepower machining center that's a 5-axis machine. It has an external coolant pump supplied by HENNIG that can do 1,000 psi and 8 gallons a minute. And we're using QUALICHEM coolant in the machine to help us out with getting the chips out of the hole. So to start us off, tell you what material we're going to be running in. It's an 8630 alloy steel that's about 225 Bernal in hardness. And we're going to run, for the first application, we're going to run an 1 3/8 diameter TA Pro P geometry, going about 7 inches deep. So it's going to be a tool similar to this one. Okay, and remember with the TA Pro, we've got geometries that are ISO specific. We have P, K, N, and M. We have P for steel, K for cast iron, N for non-ferrous applications like aluminum, and then M for stainless steels and high temps. We have a variety of different links here available, from a short link tool all the way up to 15 times D. So what we're going to do here, we're going to run into this material, once again 8630 material, about 225 Bernal in hardness, and we are going to run the first inch of cut at 220 surface feet and 10 thou per rev, and then you're going to see it back up a little bit, then it's going to come in and do the rest of the cut at 380 surface feet and 12 thou per rev, and that is going to go a total depth of cut of about 7 inches. And once it's done with that, we're going to do something else, but we're going to tell you about that when we get to it. So Adam, if you're ready, go ahead and run that. We're going to go ahead and run this 1 3/8 diameter TA Pro P geometry into 8630, 225, 230 Bernal in hardness at a beginning cut of 220 and 10. And then we're going to go back and drill the balance of it at 380 and 12. Okay, so we're going to start the cut here. And remember, whenever we're drilling, the key things that we've got to do is we've got to make the chip and we've got to get it out of the hole. The making of the chip is going to be basically on the geometry of the tool, which the TA Pro P geometry does a great job of. And then getting the chips out of the hole, that's based on the design of the TA Pro holder, as well as the amount of coolant that we have available. Okay, so to give you an idea of the load on the machine, it's running about 113% spindle load. And remember, we're going to go all the way through this cut. And whenever it breaks out on the bottom, it's going to make a little bit of noise, but that's okay. We're about halfway through the cut now. We only have about 2 inches left. Okay, and whenever it finishes up here, we'll gather up some of the chips and take a look at them. That was breakout. So we're going to go gather up some of these chips so we can show you what they look like here. So, excuse me, sir. Thank you. Okay, so there's a handful of chips off the top of the machine so you can see what it looks like. So here we go. These are the chips that we got. So you can see with that TA Pro P geometry running in this 8630, about 225-ish Bernal. You see the chip formation is good. It's nice segmented chips. It's going to be easy to evacuate, and you saw whenever the machine was running that the chips were evacuating real well. Okay, so now what we're going to do is we're going to go back into the exact same hole again. And what we're going to do is we're going to come in with an opening drill that's set to a 3-inch diameter. And we're going to run that tool at 700 surface feet and 4 thou per rev. And we're going to do that to a depth of 3 inches. Okay, so the opening drill, to remind you what that does, is it needs a pre-existing hole to do its cut, but its job is to remove a lot of material. So think of it kind of like a rough boring application, but instead of only removing, say, half or a quarter to 3/8 of an inch of material, we're going to remove from 1 inch and an eighth, or 1 3/8 all the way out to a 3-inch diameter all in one cut. So just like before, if you're ready, go ahead and go, Adam. So just like before, whenever this is done, we'll gather up some of the chips. So the opening drill, once again, it has to have a minimum diameter hole. That there's a calculation that's in the catalog that tells you how to do that. And we're going to be running this tool once again at 700 surface feet per minute and 4 thou per rev. And we're going to go to a depth of 3 inches. Okay? So once it touches down here, we'll know it. There it goes. So the load on the machine is about 125%. And once again, we're going to drill 3 inches deep at 700 surface feet and 4 thou per rev. And this is going to open that hole up from 1 3/8 out to 3-inch diameter. Okay, so it's a very good tool if I need to remove a lot of material and say a machine that maybe is not really capable of doing a hole that from solid at 3-inch diameter. I can go and basically kind of step this out, so it allows me to create those larger holes in maybe a machine that under other circumstances it wouldn't really allow it to happen. Okay, we've got about 3/4 of an inch left of drill depth to go, and remember, once we're done here, we'll go gather up some of those chips like we did with that T8 Pro a second ago, and we'll take a look at it. Okay, so we should be about done, and there we go. Okay. So we're going to come out on that cut, and we're going to gather up some of those chips and take a look at them. Thank you, sir. Okay, so, and remember, this is 8630 material. It's about 225, 230 Brinell in hardness. So here's the chips that we got with the opening drill. And remember, that was running at 700 surface feet, 4 thou per rev. And the quality of the chips is nice, and as you saw when it was running, the chips were coming out real nice. Nothing was getting caught anywhere or anything like that, and it sounded pretty good. So that was the first hole that we had. So now we're going to do a second hole profile. And with this one, we're going to start off with a revolution drill. And the revolution drill is set to 2-inch diameter, and we're going to go to a depth of 2.5 inch. And then we're going to follow that with a Combi-Line. But to give you a little bit of detail about the revolution drill, the revolution drill is a design that allows you to use one tool to do a variety of different diameters with an IC drill. So that's why it's called the revolution drill. So this particular tool, the minimum cut size is going to be 2 inches, and it's adjustable out to 2.2 inches for this particular series. And it's available in a variety of lengths, anywhere from as short as 1.5 times D to 4.5 times D, and it's going to vary by series. But the design intent with the revolution drill is it's going to run a high RPM, lower feed rate, so it allows us to take advantage of the power curve on machines to allow us to do some of those larger holes. The size range on the rev drill is from 1 7/8 out to 4-inch diameter. And as I said earlier, it's got a variety of lengths. For this tool, we're going to run in this material at 600 surface feet a minute and 4 thou per rev. It's kind of like a sister tool to the opening drill, so it's going to run kind of similar. The chip formation is going to be a little bit different because remember, now I'm cutting all the way to center, where with the opening drill there was a hole already there. So Adam, if you're ready, we'll go ahead and run this one. So remember, this is a revolution drill set to a 2-inch diameter in an 8630 material at about 225, running at 600 surface feet per minute and 4 thou per rev. Okay, going to a depth of 2.5 inches. Okay, so I'll let you know what the load is here in just a second. There it is. So the load is about 90%. So once again, it allows us to do those larger holes on lower powered machines because of the fact or not necessarily lower power, but machines with a power curve, because it allows us to take up the RPM to take advantage of that power curve, and we're running a lighter feed rate on it, so the load on the machine's not as extreme as it would be if I was using like a normal drill to do that. So we've got about 3/8 of an inch left to cut, and then we're going to come out of that, and I'll go gather up some of those chips. But as you can see, they're kind of flying all over the place, just like the way you would like them to be, and the sound of the tool is consistent, which is a good thing. So let me grab some of these. Okay, and we'll kind of show those to you. But remember, the chip form on this is a little bit different than what we saw with the opening drill, because this is what we get with the revolution drill at the same in the same material. And it makes these things like these clock springs like this, which is not uncommon for a more gummy alloy steel like this 8630 is, because it can be a little problematic sometimes getting the chips to form. But the chip that it does create, the flutes on the revolution drill are quite large, so it's easy to get those chips out of the hole, so it's not really going to be a problem to do that. So for the second part of this particular hole, what we're going to run is our Wohlhaupter Combi-Line tool. And the Combi-Line tool is going to take it from a 2-inch hole to a 2.25 inch hole. Okay, and the way that it's going to do that is the Combi-Line is set up where I have, let me show you under the screen here so you can see a little bit better. On this side, I'm going to do my roughing work, and then on this side, I'm going to do my finish work. So over here, I'm going to set this just like you would with a rougher. I'm going to use this screw here, and I'm going to set the diameter on this. So it's going to be close, but it's not going to be, you know, within tenths precise. But then whenever I do this side, I actually have a dial indicator just like I would have on a finish boring tool that allows me to get a very exact size. And you can see, like, this is solid, and then it's got the slide is here, which is going to be adjusted with this dial. Okay, so what that's going to allow us to do is that we're going to run this tool, and it's going to take it from a 2-inch to 2 1/4 inch, and I'm going to have a rougher to do like a rough boring pass, and then I'll also have the finish pass get done at exactly the same time, instead of running a rough bore cycle and then come in with a finish bore cycle using 2 different tools. So it's going to do it in less time, and maybe just as importantly, depending on your application, if you're limited on tool positions, it saves you a tool in the machine. So Adam, if you're ready, we'll go ahead and run this one. Okay, and once again, we're going to run this at 450 surface feet per minute, 3.5 thou per rev, and we're going to go to a depth of 1.5 inches with the Combi-Line tool. So remember, this is going to take that 2-inch diameter rev drilled hole that we just did, and we're going to open up to 2 1/4 using the rough and finish pass that goes with this. So we're opening up that hole about 6 millimeters. So the way that this should be set would be to do 60% of the cut with the roughing tool and 40% of the cut with the finishing tool. Let the rougher do most of the work, and basically the finisher comes in and cleans it up. The finish that you get with this should be of the same fit and finish as what you would expect any fine boring tool to produce. And what I did was I removed more material and less operations, and I saved myself a tool station. Okay, so we are just about done with this one. Okay, and there it is, it's all done. So we're going to take that out. Okay, now I'm not going to gather up the chips from this, because with a boring tool, the chips that it's going to produce are going to be smaller chips, and quite frankly, with all the coolant that we have going on here, it's going to be kind of difficult to get those chips out, to gather them up, to take a look at them anyway. So that was hole profile number 2. So we took a 2-inch diameter revolution drill and we opened it up to 2 1/4 inch diameter using a Combi-Line tool. Okay. For hole profile number 3, we're going to use our APX tool to create a 2-inch diameter hole going 5 inches deep. Okay. Now, the reason you would use the APX is it's basically under the same general idea as like a revolution drill or an IC drill would be, which is going to be high speed, lower feed rates, so I can take advantage of that power curve just like I could with the rev drill. But with an IC drill, based on the way that it's a single effective cutter, so I've got a cutting edge on one side and it's open on the other, it becomes inherently unstable at depth. Okay, so an IC drill, once you get above about a 3 times D depth of cut, it creates a situation where the tool has a little bit more difficult time holding tolerance, finish, things like that. So the Apex is kind of designed to come in applications where the revolution drill or another IC drill would not be able to be part of the equation based on the depth to diameter ratio. So the lengths of the Apex tool are anywhere it's a 3, 5, 8, and 10 times D. Okay, so the way that it works is it's going to have a TA. Pull it out here, we'll kind of hold it under the camera so you can see it a little better. So it's going to have a TA in the front, and what that TA does is it creates stability for the inserts doing the cut on the outside. Okay, so instead of the tool wanting to move around the point of the TA or the Gen 3, because we do make Apex with Gen 3 pilots, it creates stability for this, so now I can go for deeper drill depths. Okay, so once again, that's for 3, 5, 8, or 10 times D. The tool we're going to be using is a 2-inch diameter, so it'll be the same diameter as what the revolution drill did. But instead of only going 2.5 inches deep, we're going to go 5 inches deep. If you're ready to go ahead. Okay, so this one is going to run at 500 surface feet a minute and 7 thou per rev, going for a depth of 5 inches. So if you notice that compared to the revolution drill we ran just a minute ago, it ran at 600 surface feet and 4 thou per rev. So it's a little bit less on the surface footage per minute, but it does have a higher feed rate in relation to the revolution drill. Okay, now Apex is available in sizes from 33 millimeters, which is about 1.299, all the way up to a 4-inch diameter. Okay, when you get to 2 3/4 and above, we go to an unbalanced cutter because of the diameter of the difference between its TA or Gen 3 at the front and what the inserts are cutting on the outside. So since we unbalance that tool, we actually do put wear pads into the body or into the head to keep it from moving around. So it's still available up to a 10 times D depth of cut, but it just does it in a slightly different way. That's also going to reduce the horsepower draw that you have because of the fact it's going to go to a single effective cutter. So it's going to run at a little bit lighter feed rate, but I can still do depths that I wouldn't be able to do with a standard IC drill like the revolution drill. Now the load on this was about 122%. So we're going to gather up some of these chips from the APX to show you what it looks like. And There are chips for the outside that look one way, and I'm going to see if I can find a couple of TA chips to show you, because they're quite a bit smaller. There's a couple of them, I do believe, to show you those. Oh, there's one. Okay, just to give you an idea of the comparison between the size of the chips that we're dealing with here. So if I can get a hold of it, I'll show it to you. Okay, so it's pretty small. I don't have a big selection of those because there's plenty of coolant going through that tool, so it's throwing the chips everywhere. So these are the chips coming off the APX, okay, and you can find it here. Here's the chip that was made by the TA on the front end of that. Okay, so the TA establishes the cut. Move this over here. The TA establishes the cut and provides the stability that you need to create those longer drill depths, but then the outboard inserts are what creates the bulk of the cut and takes the chips out. So once again, that tool is running at 500 surface feet per minute and 7 thou per rev. Okay, so moving on to the next hole profile. Okay, now we're going to show you our Vortex drill, which let me show you that one real quick underneath the camera before we get into the run of this. Okay, so this is our Vortex. This is more of a traditional IC style drill because the diameter of the body is going to determine my cut diameter. Okay, but what's different with the Vortex drill is the inserts that we use are actually four-sided because I'm going to use two of the sides here for my inboard cut. Then I'm going to need to use the opposite two sides to do the outboard cut. And the reason why we do that is the outboard, I need positive cutting geometry to create the chip form that I want to have. At the center of the tool, since you have zero surface footage at the center, what you're going to get there is you need strength in order to have the tool hold together for that cut. So we're using the strong parts in the middle, and then we're going to roll it to the sharp parts for the outside. Now what that's going to do though, if you want to go ahead and run, you can. So what that's going to do though is it's going to create a situation where I've got two different chips. I've got an outboard chip and an inboard chip, which I will show those to you. The inboard chip is going to be bigger, okay, because of the fact it doesn't have geometry there, because at the center of the tool, what I need there is strength. Okay, now the drill that we're going to use is an 1 5/8" diameter Vortex, drilling 5 inches deep, because this is a 4x-D tool. The speed and feed that we're running this tool is 500 surface feet per minute and 4.5 thou per rev. So it's going to take about a minute to drill this hole. But if you look at it while it's running here, and you can hear, it's got the same pitch as it's going through this cut. So what that means is my load is stable. And right now it's at 58% spindle load. Okay, remember this is an 1 5/8" diameter. Okay, so my spindle load is nice and stable, and you see the chips coming out and expelling quite nicely because we have a decent amount of coolant pressure available to us thanks to that HENNIG 1000 PSI or 8 gallons a minute pump. Okay, now you just heard that one chip come out and kind of hit the wall there. The center chips are going to be bigger and heavier, so they're going to make a little bit more noise than the outboard chips do. And I'll show that to you whenever we're all done here. Okay, so we have about 1/4 of an inch left. Okay, and we are done. So we're going to take that out, and we'll gather up some of those chips to show them to you real quick. Okay, thank you, sir. So here's the center, so I can show you that. And here's some of the outboards, so I can show you those as well. Because like I said, remember it's going to make two different chips because the geometry is going to be different between the two. Okay, so here's my center chip, and you can see it's just like kind of a tight spiral that it creates. But remember, at the center of the tool, I want strength there, so it's not going to be as good a chip for me. Okay, but then on my outboard, you can see I get a really nice chip on the outside because on the periphery, what it's going to have is positive cutting geometry out there to get the chip to form better. Okay, so that's an 1 5/8" Vortex drill running 5 inches deep. We're going to follow that with a twin cutter from Wohlhaupter, so this would be a rough boring tool. Okay, and we're going to run it at 425 surface feet per minute and 6 thou per rev, and it's on the same level. So this is going to be like a twin bore. So we're going to basically we're going to increase our feed rate. You can go ahead and run that. We're going to increase our feed rate because I have two inserts that are cutting the same diameter. Because with a twin bore, I have the option of setting them to the same diameter, running twice the feed rate, or staggering the diameter. And when I do that, what I can do is I can remove twice as much material. So the Vortex was an 1 5/8". The twin cutter is set to 1 3/4". So we're going to be removing 1/8 of an inch off the diameter of this hole. Okay. Now you can hear this tool's a little bit noisy whenever it ran. But the reason that it was, and I'm not going to gather the chips up for that either, so it's okay. The reason for that is this material, quite frankly, can be a little bit grumpy sometimes. I can run it in one application, it's quiet, and I put it in another hole in a different part in the block, it's going to make a little different noise. But remember, what I'm doing when I'm doing rough cutting, what I'm trying to do there is I'm just trying to open the hole up. If I want to have a fine finish and a fine tolerance, that's where I'm going to use a finishing tool like a Combi-Line or one of the other Wohlhaupter finishing products, and we're going to show you one here in just a couple minutes. Okay? So moving on to hole profile number 5. Speaking of showing you a finishing tool from Wohlhaupter, we're going to start this off with an 1.25" diameter TA Pro drill, because in the first application that we ran 1 3/8" diameter TA Pro. So this is an 1.25" TA Pro P geometry. We're going to run 380 surface feet and 11 thou per rev to a depth of 3 inches. Now what we're going to do is where we just ran that Vortex and then the twin cutter, we're going to put 3 holes, like in a triangular shape, around that hole, kind of like what you would do for a bolt circle, for example. We're going to use that TA Pro P geometry to drill all 3 holes, once again going 3 inches deep. Then we're going to come in with a Wohlhaupter 420 series boring head. It's a finished boring head to take it from 1.25" out to 1.299, which is approximately 33 millimeters, and we're going to do 2 of those holes. And then the last hole, we're going to come in with a burnishing tool set to 33 millimeters, and we're going to burnish the last hole. So we're going to drill all 3, we're going to bore 2 of them and burnish 1. Okay, so if you're ready, we're going to go ahead and run the TA Pro P geometry, 380 surface feet, 11 thou per rev. It's an 1.25" diameter, or 1.25" inch diameter, 3 inches deep, 3 holes. Okay, so we're going to do that first. Okay, so just like before, I'll let you know what the load is. Okay, so there it goes. The load is 89% on the tool. Okay, and you see the chips are coming out great. Sounds pretty good. Everything looks pretty decent for us here. Okay, so that's the first hole. Now it's going to do 2 more. Because remember, we're going to leave 1 as a drilled hole. We're going to bore 2 of them and then burnish one of those 2 bored holes. Okay, so there goes the TA Pro for the second hole. Once again, still at 89%. The sound is still good. You can see the chips flying out, which is exactly what you want to see whenever you're running a drill. Because remember, the 2 things that I have to do to be successful is I have to make the chip and I got to get it out of the hole. So making the chip has a lot to do with the geometry of the TA Pro P. Getting it out of the hole is the redesign of the TA Pro holder. Larger flutes, better coolant holes, which is going to give me 25% more flow at the same diameter. And I'm going to gather up a couple of those chips just to show you that they look the same as what the 1 3/8" did. Okay. Just show you real quickly here. So, thank you, sir. So here's the chips that we got with the TA Pro there. Okay, so they look the same as what we had before. So remember, that was an 1.25" TA Pro. Now we're going to come in with a Wohlhaupter fine boring head that's in the 420 series. Okay, and the final bore size is 1.2995 or 1.2952 is the size that we're going to do. And we're going to do that for 2 holes, and we're going to do that at 450 surface feet and 3.5 thou per rev. So whenever you're ready, Adam, go ahead. And we're going to do that on 2 of those 3 holes. Okay. So the Wohlhaupter 420 is a fine boring tool that's going to have a range of sizes to it. And then, you know, to do a different range of sizes, I would buy a different boring head. Okay. So this is a really good fine boring tool. It's going to give you good surface finish. It's going to give you tight tolerance. It's going to repeat really well. And once again, we're running this at 450 surface feet, 3.5 thou per rev, and we've got about 3/4 of an inch to go on the first hole. And remember, we're going to go ahead and do a second one of these as well. Okay, so this is removing, you know, once again, about 20 thou a side or so on a finished bore pass. Okay, which is a fairly common amount of material to remove. It's usually around the 64th or so. So that's pretty much a common thing to do on diameter. Okay, so we're going to come in and we're going to feed this in again. Now with Wohlhaupter's boring products, Wohlhaupter has a full line of inserts to go with that. So if you have a specific need, or you're having chip formation problems or something like that, we have a wide variety of different boring inserts available to try to custom fit it to your application. Okay, so if you're not sure, you can contact our application engineering group or your local FSE. Okay, and then the next tool that we're going to use is going to be our burnishing tool. Okay, now a burnishing tool looks like this. Okay, and basically what a burnisher does is it doesn't actually cut anything, and I'll show you this up underneath here. It basically just has a series of rollers, and these rollers ride on a cone, which I'll kind of turn this here so you can see there's the cone right here. So there's a cone in here that's shaped like this. Whenever we go down into the hole, the cage actually kind of moves up that cone a little bit, which brings these rollers out into contact with your workpiece, and all it does is it acts, the best way I can describe it's like a steamroller. It's just going to take the peaks of your application and smash them down into the valleys to make it a more true, a more smooth surface. So it's going to greatly improve the surface finish. And since I'm cold working that product, it's actually going to create a slightly harder surface as well. So applications that would use something like this would be like a hydraulic cylinder or a master cylinder for a car, something along those lines. Okay, so we're going to run this at 500 surface feet a minute. No, I'm told you're wrong. 395 surface feet a minute and 60 thou per ref. So this is just going to come down real quickly, act like a steamroller, kind of smash those peaks into the valleys and then come out. Okay, so if you want to go ahead at them, you can. But whenever this runs, what you want to have prior to doing your burnish work is you have to use either a boring tool or a reamer. You have to make sure you true the hole up and you get the finish somewhere between a 32 and a 64 RA inch finish, because what that does is that creates a situation where I have a very nice peak and valley kind of situation. So I got something to mash down in there. You have to make sure as well that you're in a material that has some malleability to it, because I have to be able to do that smashing that we talked about just a minute ago. Okay, so materials under 40 Rockwell, think like steels, aluminums, cast iron is not a great material because it isn't terribly malleable. Stainless steel is good. Okay, so there's a variety of different materials that you can do that would give you a good outcome. So we'll show you that if we're able to here in a minute. We're going to go ahead and move to profile number 6. So profile number 6 is using our AccuPort 432, which is, well, I don't have, oh, here it is. I do have one out here. So here's the AccuPort 432, okay? So what the AccuPort 432 is designed to do is you're going to TA pilot to drill the front end, then you're going to create the seal area for the port, then you're going to create the spot face, and it does all this work at once, and it holds finish tolerance, okay? So the types of applications that you're going to use that for would be hydraulic manifolds, hydraulic cylinders, things like that, because now I got to plug in a hydraulic port into that. It's made to an SAE or an ISO standard port form, okay, and we have several different ones, and we'll tell you about them here in a minute. But the idea is I'm going to come in and I'm going to do that. I'm going to create that whole form at once. Then all I have to do after that is come in with a threading tool and thread the hole, and then drill another hole to intersect my feeder line, and the application's done. In traditional machining operations, the way that it normally gets done is they come in with a drill, then they come in with a roughing tool, and then a finishing tool. Because the roughing tool used to be a finish tool, but then whenever they regrind it, now it's no longer in a hold finish form, so they use it as a rougher to extend the life of the finishing tool. Okay? The people that normally do this are going to be people using solid carbide or brazed carbide tools, or even a solid high-speed steel form tool that's cut to that shape. Now, what we've got are replaceable inserts that are either high-speed steel or carbide. They're going to be coated, so we're going to run higher penetration rates. There's no regrinds that get done, and we're going to do the finish work all in one step. So I'm going to go from 3 operations to 1. So that's a big advantage. Now, the types of port forms that we can do is J1926, which creates a UN style thread, ISO I6149, which creates a metric thread. They're very similar in shape, form, fit, and function, except the type of thread is different. I got inch threads or metric threads. And on the metric one, you have the option of having an identification ridge. So if I have a mixture of inch and metric threads on the manifold, there'll be an ID ridge on the spot face that'll let you know that those particular threads are going to be metric. Okay. The third type that we have is AS5202, or the mil spec style. It's commonly used in aerospace applications, and what it has is a slight metal on metal contacts that are just an O-ring. And So the difference between those two is the I-6149 and the J1926 are designed to hold back a pressure of roughly about 3,000 psi. The AS5202, the mil-spec style, is designed to hold back a much higher pressure, like twice that amount, like 6,000 psi. It is commonly used in aerospace applications and some military applications as well. The fourth style that we have is the G173.1, which is the John Deere specification, and it's very similar to the I-6149, but they tweak some of the dimensions specifically for John Deere applications. So we offer that as well. Okay? So the tool we're going to use first is a J1926 number 14 tube size, and it's going to create roughly like a inch 200 thou-ish pilot. Okay? And it's going to run at 375 surface feet a minute and 8 thou per rev into this 8630, this 230 Burnell. Whenever you're ready, Adam, we can go ahead and go. And remember, what it's going to do is it's going to create the pre-drill, the port form itself, and the spot face all in one operation. Okay? Because then we're going to follow that up with one of our thread mills, but I got to tell you a little bit about that before we run it. Okay, so let me get you the load on this. So it's about 60% on the pilot. And then whenever everything touches down, that number is going to go up. It goes up to pretty close to 100. Okay, and the reason that it does that is it's cutting a lot more material. Okay, so therefore it's got a heavier load that it's going to do. So we're going to do 2 of those. We did the first one. Now it's time for the second one to come in. Okay, and the depth of this is right around 1 inch, so it's not a real deep hole. Okay, and I will show you the chips that came off that. Okay, once we complete the cycle here. And then we'll talk a little bit about that thread mill. Okay? So let's open up the door and we'll grab a couple of those chips. Okay? Because it does make a different chip, because there's one here for the spot face, so I want to show that to you. And then we've got the chips that get created on the front end. Okay? So I'll show you a couple of these here. So this is what we have. So the pilot is going to make chips that look like this. This is coming off the spot face, but the spot face is usually only about a 32nd of an inch deep, so it doesn't really get a chance to generate like small segmented chips, but I'm only going, this deep with it, so it's going to be fine to do that. Okay, so that's what the AccuPort creates. So now what we have set ourselves up to be ready to do is now what we're going to do is we're going to come in and thread this hole. So we're going to use our AccuThread 856 thread mill to create an 1 3/16" 12 UN thread to finish off this J1926 number 14 tube size. Okay, so this thread mill is going to come in running at 500 surface feet a minute, 1 thou 3/10 port per tooth. I want to say that I think it's a 5-fluter is what we're going to be doing. You can go ahead and run that. This is going to be relatively quiet. And we're going to do this in 2 passes. The reason why we're going to use 2 passes is because this is an alloy steel that's roughly in the mid 200s of hardness, and whenever you're doing a thread mill, the enemy of a thread mill is going to be deflection. So in order to minimize that deflection, we're going to come in with the first cut at 75% engagement, and then we'll come in with the second pass at full engagement to create that thread. Okay? So remember, the way a thread mill works is a thread mill is just a mill. So it just has the shape of the thread. So it would be the form of the thread, and the pitch is determined by the thread mill itself. The actual size of the thread that it creates, like in this case, a 1 3/16, is determined by the path that the tool takes. So what we need to have whenever we're running this is I have to have the ability to run an X, Y, and Z at the same time. So I got to have 3 axis simultaneous movement or helical interpolation. It has to be activated or available on the machine. Okay, so as long as I can do that, because the actual creation of the threads is the path that tool takes through that workpiece. Okay, so it's going to come in Z, and then it's going to go down, and it does 1 full revolution, and that's what creates the threads. Okay, in the time that I was talking there, we actually threaded 2 of them. So what we did was we created the port form, and we threaded the port form for 2 different ports in the amount of time that we've been running this last part of this demo. Okay, so that actually concludes the demonstration that we have for you today, and we will hopefully be able to show you what the finished part looks like at some point in time, because it's kind of hard to see from behind me here, and inside the machine you just see a little bit, but Hopefully what you've learned is that Allied has a wide variety of tools that are available to you. We run in sometimes difficult material to machine, and we can basically do everything from drill the hole, we can ream the hole, bore the hole, burnish the hole, thread the hole. So if you have any hole making needs, please contact your local FSE or contact our application engineering department. Thank you and have a good day.